The invention of dynamite in 1867 by Alfred Nobel was a groundbreaking moment in the history of explosives. Before dynamite, nitroglycerin was widely known as a powerful explosive but was extremely dangerous to handle due to its volatility. Nobel, a Swedish chemist and engineer, sought to find a way to harness the immense power of nitroglycerin while making it safer to transport and use. Through his research, he discovered that mixing nitroglycerin with an absorbent material, such as diatomaceous earth, stabilized the compound. This mixture created a malleable substance that could be shaped into sticks and safely handled without the risk of accidental detonation. Nobel named this invention dynamite, derived from the Greek word dynamis, meaning power. His invention marked a turning point in the fields of mining, construction, and demolition, allowing for controlled and efficient explosions that were far more powerful than previous methods like black powder. Dynamite's potential was quickly recognized by industries that needed to break through rock, build infrastructure, and perform large-scale earthworks. As a result, Nobel's dynamite rapidly gained popularity, transforming industries and accelerating the pace of progress during the Industrial Revolution. Despite the success and widespread adoption of dynamite, Alfred Nobel was personally troubled by its potential misuse. While his invention was intended for peaceful applications, it was soon recognized for its destructive power and adapted for military purposes. Nobel's concerns over the negative impacts of his invention later inspired him to establish the Nobel Prizes, hoping to leave a legacy that focused on rewarding positive contributions to humanity. The power of dynamite comes from its key component, nitroglycerin, which is an oily, highly unstable liquid known for its ability to release immense energy. Nitroglycerin is a nitrate ester, which means it contains a combination of nitrogen, oxygen, and carbon molecules that react violently when exposed to heat or shock. In its pure form, nitroglycerin is extremely dangerous to handle because it can explode with even a small impact. However, by absorbing it into diatomaceous earth, the explosive becomes safer to transport and control. When a stick of dynamite is detonated, typically using a blasting cap, the nitroglycerin undergoes a rapid chemical decomposition known as detonation. This process releases gases such as nitrogen, carbon dioxide, and water vapor at an astonishingly fast rate. The sudden expansion of these gases creates a high-pressure shock wave that can break apart solid materials like rock or concrete. The effectiveness of dynamite lies in the sheer speed and intensity of this chemical reaction, which produces a powerful explosion within milliseconds. The invention of dynamite also led to innovations in how explosives were used. Miners and engineers were able to drill more precise holes, insert dynamite, and achieve controlled blasts that reduced the risks associated with traditional methods. The stability of dynamite, combined with its explosive strength, made it ideal for large-scale projects like tunnel construction, road building, and the clearing of land for railways. Moreover, Nobel's invention sparked further developments in explosives technology, such as the creation of gelignite, a more powerful version of dynamite that could even be used underwater. In summary, the chemistry behind dynamite allowed for the controlled release of immense energy, making it one of the most significant technological breakthroughs of the 19th century. Its ability to transform industries while still posing safety challenges highlighted the delicate balance between innovation and risk in the field of explosives. Dynamite's impact on industrial progress cannot be overstated. Its introduction revolutionized industries that required large-scale excavation and demolition, particularly mining, construction, and civil engineering. Before dynamite, the mining industry relied on labor-intensive and dangerous methods to extract minerals from deep within the earth. Black powder, the primary explosive used before dynamite, lacked the power and precision needed for major projects. Dynamite changed all of this by offering an explosive that was not only significantly more powerful but also more predictable and easier to control. In mining, dynamite allowed workers to bore deep into rock formations, blast away tough material, and access previously unreachable mineral deposits. The efficiency gained by using dynamite drastically reduced the time and effort required for mining operations, leading to higher productivity and profits. It became an indispensable tool in extracting coal, precious metals, and other valuable resources. Major mining operations around the world quickly adopted dynamite for its ability to streamline operations and improve safety, despite the inherent dangers associated with its use. The construction industry also saw a significant boost from dynamite. Large infrastructure projects like railroads, tunnels, and bridges benefited from the ability to clear vast amounts of land quickly and efficiently. For example, the construction of the Transcontinental Railroad in the United States, completed in 1869, was made possible in part by dynamite, which helped workers blast through mountain ranges and other difficult terrain. Similarly, in Europe, the construction of tunnels through the Alps relied heavily on dynamite to break through the dense rock. One of the most iconic uses of dynamite in construction was during the building of the Panama Canal, where its power was essential in excavating millions of cubic meters of rock and earth. Dynamite-enabled projects like the canal not only reshaped global trade routes but also demonstrated the vast capabilities of this explosive in transforming landscapes on a massive scale. While dynamite revolutionized industries, its adoption by militaries and insurgents transformed it into a symbol of destruction. Although Alfred Nobel originally intended for dynamite to be used for peaceful purposes, the explosive power and portability made it a natural fit for warfare. By the late 19th and early 20th centuries, dynamite had been adapted for military use, particularly in the form of landmines, grenades, and other explosive devices designed for sabotage and demolition. In warfare, dynamite was used to destroy enemy fortifications, bridges, and railways, crippling supply lines and infrastructure. Its efficiency made it a critical tool in conflicts such as the Boer War, the Spanish-American War, and later, World War I. Soldiers could carry dynamite into battle and use it to achieve strategic victories by blowing up defensive structures or disabling key transportation routes. Naval warfare also saw the use of dynamite in torpedoes and depth charges, adding another dimension to its destructive power. Beyond the battlefield, dynamite became notorious for its role in terrorist attacks and insurgencies. During the late 19th and early 20th centuries, anarchists and revolutionary groups across Europe and the United States used dynamite in high-profile bombings aimed at disrupting political and economic institutions. These acts of violence, often targeting government buildings, banks, or public places, associated dynamite with social unrest and rebellion. Figures such as Emma Goldman and groups like the Russian nihilists embraced dynamite as a weapon for change, further cementing its legacy as a tool for both industrial progress and violent upheaval. This dual nature of dynamite, as both a creator and destroyer, posed ethical dilemmas for Alfred Nobel and others involved in its development and use. Nobel himself was deeply troubled by the way his invention was being exploited for violence. In response, he sought to atone for the negative consequences of dynamite by establishing the Nobel Prizes, which continue to recognize advancements in science, literature, and peace. Nobel's hope was to ensure that his legacy would ultimately be one of progress and benefit to humanity, despite the dark side of his invention's history. Today, dynamite's role in warfare has largely been overshadowed by more advanced explosives and technologies, but its association with both industrial achievement and violent conflict remains an important chapter in its history. The use of dynamite in terrorist attacks and sabotage throughout the 19th and 20th centuries highlights the complex and often contradictory legacy of one of the most powerful inventions of the modern era. In the modern era, dynamite remains a vital tool in industries such as mining, construction, and demolition. However, with the advent of newer and more specialized explosives, its usage has become more selective. The primary reason dynamite is still employed today is due to its effectiveness in breaking apart tough materials such as rock, concrete, and dense earth. Despite the emergence of safer alternatives like ammonium nitrate fuel oil, ANFO, explosives, dynamite's unparalleled explosive power ensures that it remains indispensable in certain applications where precision and force are required. In contemporary mining, dynamite continues to be one of the most effective means of breaking through hard rock. Mining operations in sectors like coal, copper, and precious metals rely on dynamite for extracting materials buried deep within the earth. Dynamite's use is especially critical in open-pit mining, where large sections of earth and rock need to be blasted away to expose the underlying minerals. In quarries, dynamite is used to extract stone and gravel for construction materials, such as limestone, granite, and marble. The precision with which dynamite can be placed and detonated allows operators to produce high-quality blocks of stone with minimal damage to the surrounding material. One of the major shifts in the use of dynamite today, compared to the past, is the enhanced focus on safety and environmental concerns. In mining operations, controlled explosions using dynamite are carefully planned with computer models to predict the outcome of the blasts, ensuring minimal damage to the surrounding ecosystem and reducing the risk of accidents. Advances in blasting technology allow for more targeted detonations, which decrease the amount of dust, noise, and seismic impact produced by the explosions. This is crucial in regions where mining occurs near populated areas or sensitive environments. In construction, dynamite continues to be a valuable tool for large-scale demolition projects. When buildings, bridges, or other structures need to be removed, dynamite is often used to perform controlled demolitions. Demolition experts place dynamite charges strategically within the structure to bring it down in a controlled manner, minimizing debris spread and collateral damage to nearby buildings. This precision is critical in urban areas, where space is limited and safety concerns are paramount. Controlled demolition using dynamite is also used in infrastructure projects, such as the removal of old dams, tunnels, and roadways. These projects require dynamite's explosive force to dismantle reinforced concrete, steel, and other tough materials. One famous example of dynamite's continued use in construction was the demolition of the Seattle Kingdome in 2000, where over 1,800 pounds of dynamite were used to bring down the stadium in a matter of seconds, marking one of the most iconic modern-day demolitions. With the use of dynamite comes the necessity for strict safety regulations to protect workers, the public, and the environment. The dangers associated with explosives like dynamite, especially their potential for accidental detonation, have led to the development of rigorous safety protocols at both national and international levels. Organizations such as the Occupational Safety and Health Administration, OSHA, in the United States and similar regulatory bodies worldwide oversee the production, transportation, and use of explosives, including dynamite. One of the most important safety measures is the licensing and training required for individuals handling dynamite. Only certified blasters with specialized training are allowed to handle and detonate dynamite in industrial settings. These professionals must undergo extensive education on the physics of explosions, the proper placement of charges, and the timing of detonations to ensure safe and controlled blasts. In addition to training and certification, there are strict regulations governing the storage and transportation of dynamite. Explosives must be stored in secure facilities, often located in remote areas, to minimize the risk of accidental explosions. Transporting dynamite is also tightly regulated, with strict rules on how it can be loaded, handled, and shipped to prevent accidents during transit. In recent years, there has been a push towards developing even safer alternatives to dynamite. Innovations in explosives technology have produced new materials that offer similar power but with reduced volatility and environmental impact. For instance, the development of ANFO, which combines ammonium nitrate with fuel oil, provides a safer and more stable explosive option for many industrial applications. ANFO has largely replaced dynamite in many operations because it is easier to handle, less sensitive to shock, and can be produced in bulk at a lower cost. However, dynamite's superior explosive force in specific situations ensures that it remains in use. Modern usage of dynamite is increasingly tied to environmental regulations that aim to minimize the ecological footprint of its use. Environmental impact assessments, EIAs, are now standard procedures before any large-scale use of dynamite, particularly in mining and construction. These assessments evaluate the potential effects of blasting on local ecosystems, groundwater, wildlife, and air quality. The aim is to reduce the disruption caused by explosions and ensure that post-blast environments can be restored or rehabilitated. In recent decades, there has also been a growing focus on reducing the carbon footprint of dynamite production and its environmental aftermath. For instance, blasting engineers now use specialized techniques like vibration monitoring and precision timing to limit the energy released beyond what is necessary for the task at hand. This reduces the production of harmful byproducts like dust and toxic gases, making dynamite a more environmentally responsible tool in comparison to past practices. While dynamite has largely been surpassed by newer explosives in many fields, its potent legacy as a tool for progress and innovation remains intact. The Industrial Revolution, massive construction projects, and advancements in mining all owe a great debt to the invention of dynamite. In the modern era, its use is carefully regulated and accompanied by rigorous safety measures, ensuring that it continues to play a crucial role in select industries while minimizing risk. As environmental concerns take center stage, the responsible use of dynamite remains a key part of the conversation surrounding industrial progress and sustainable development.